Hi, this is Mrs. Wiederholt, and welcome to my lesson video on rational functions, asymptotes, and wholes. Now let's get started. First, let's go over the definition of a rational function. A rational function is a function with polynomials in the numerator and the denominator. And what is a polynomial? Well, remember, a polynomial is an expression that contains one or more terms. If it only has one term, it's called a monomial. If it has two terms, it's a binomial. Three terms, it's a trinomial. And then anything after that, we just refer to as polynomials. But as a whole, we refer to the whole category of these expressions as polynomials. Next, let's talk about wholes. Now, this is a new term for you, and a whole is literally just a hole in your graph or the curve. And you could also say it's a point where the line doesn't exist. In this video, we are going to learn how to find the wholes in your rational function, and we are going to learn how to express the domain and range of a rational function when there is a hole in that function. Now let's review asymptotes. Now, a vertical asymptote is an invisible vertical line that your graph or curve never crosses or touches. We express the vertical asymptote as a dashed line. The horizontal asymptote is an invisible horizontal line that your graph or curve never crosses or touches. And we express that also as a dotted or dashed line. Now let's figure out how we can find these three things from an equation. We will use the example 3x plus 1 times x plus 4 divided by x minus 7 times x plus 4. In step number 1, you are to factor the denominator and the numerator. Well, if you look at our example, it has already been factored. So we could say that that's done. We don't have to do that step in this one. In step number 2, you were to cross out the common factors. So I can cross out x plus 4 divided by x plus 4, which will leave me with 3x plus 1 divided by x minus 7. Now before we talk about step number 3 and how to do it, let's talk about wholes for just a second. I mentioned on the page before that they represent a point where the line doesn't exist, or a hole in the curve. So let's just do a little graph just so you can get a picture of what we're talking about. In a graph, we could have a curve like this, and then there could literally be a hole right there, but then the graph continues on. Okay? So when we talk about a hole in the graph or in the curve, that's what we're talking about. Now let's talk about step number 3. The first thing it says is that denominators that cancel are wholes. Well, if we look at our denominator in our example, x plus 4 was canceled out or crossed out. So we can take that x plus 4 and we can set it equal to 0 and solve for x. Subtract 4 from each side and we have x equals negative 4. This is the x-coordinate of our hole. Now, what if you had two terms in the denominator that were crossed out? Well, that would mean you would have two holes in your graph. So, going back to this one, how do we find y? Well, if you look at the second part of step number 3, it says to plug into the final function, meaning plug the x value into the final function, which is this one right here. It's the reduced one, the simplified one, and then you will plug it in and solve for y. So let's do that. We would have 3 times negative 4 plus 1 over negative 4 minus 7. Now remember, this is equal to y. F of x up here is the same thing as y. So now let's simplify it. 3 times negative 4 is negative 12. Negative 12 plus 1 is negative 11. And then negative 4 minus 7 is also negative 11. And so this simplifies to positive 1. So what that means is the ordered pair for this whole is negative 4, positive 1. Now the fourth step tells us how to find our vertical asymptotes. So let's look at it. Denominators that don't cancel are the vertical asymptotes. Well, let's go up here to our original example, and our denominator that did not cancel or cross out is x minus 7. So we're going to take x minus 7 and set it equal to 0 and solve for x. So if you add 7 to both sides, we have x equals positive 7. So this is our vertical asymptote. Now, what would that look like on a graph? Well, you would go to the right 7 units and you would draw a vertical dashed line going straight through where x equals 7. Now it's your turn to try one. So pause the video, you try the next one, and then turn the video back on to see how you did. Okay, hopefully you've had time to work this one out, and let's go over it together and see how you did. First thing we need to do is factor the denominator and the numerator. And as you can see, this one has already been done. There was nothing to factor. So we could move on to the second step, which is to cross out the common factors. Well, up here in blue, I did just that. I crossed out the x minus 4 divided by x minus 4. Now when you do that, this is what you're left with, and I wrote that right here. Okay? Now going on to step number 3, the denominators that cancel are the wholes. So my denominator that canceled was x minus 4. So that's why I set x minus 4 equal to 0, and then I solved for x. I got x equals 4. Now, 4 is the x coordinate of my whole. So I need to plug that 4 in to the final function, meaning the reduced one, so I can find out what my y value is. So that's what I did. Here's y equals, and instead of 2x, I've plugged in the 4 for the x. So 2 times 4 plus 3 divided by 4 minus 1. And that equals 11 thirds. So that means y equals 11 thirds. And so that is the y coordinate of my whole. So here's the ordered pair for the whole. 4, 11 thirds. Now, let's go ahead and look at step 4, which is showing us how to do or find the vertical asymptotes. Now, the denominators that don't cancel are the vertical asymptotes. So I go up here, and x minus 1 is the denominator that did not cancel. So that's what I set equal to 0, and then I solve for x. So x equals 1, which means my vertical asymptote is x equals 1. Now let's learn how to find the horizontal asymptotes. First, let's look at the green example. If the degree of the top polynomial is less than the degree of the bottom polynomial, then you have a horizontal asymptote at y equals 0. Well, let's look. How do you determine the degree of a polynomial? Well, you have to look at the exponent. So in the numerator, my largest exponent is a 3. So that's the degree of that polynomial. It's called a polynomial to the third degree. Now, if you look at the denominator, the exponent or the largest exponent of that polynomial is 4. So this is a polynomial to the fourth degree. Well, the bottom polynomial is a larger degree than the top polynomial. So that means your horizontal asymptote will be at y equals 0. Now let's look at the blue example. If the degree of the top polynomial equals the degree of the bottom polynomial, then you have a horizontal asymptote at y equals a over b, where a is the coefficient in the polynomial that's in the numerator, or the first term that's in the numerator, and b is the coefficient of that first term that's in the denominator. So it would look like this. We would have y equals, and then we said a is the coefficient which is 6, and then this coefficient, which is 2, and then we would just reduce. 6 divided by 2 is 3. So this horizontal asymptote would be at y equals 3. Now let's look at the red example. If the degree of the top polynomial is greater than the degree of the bottom polynomial, then you have no horizontal asymptote at all. So let's look at our degrees here. If I look at the first term, 6x to the third, well, that exponent of 3 is my largest, so that is a polynomial to the third degree. And if I look at my denominator, my largest degree is 2, so that's a polynomial to the second degree. Now, my numerator's degree is greater than my denominator's degree, so that means there is no horizontal asymptote. So you could write none, or you could write NA for not applicable. Now let's try to put all of this together. First, I want to find my wholes, so in order to do that, I need to factor the numerator and the denominator. So I will have 4 times x plus 3 in my numerator, and my denominator, my factors are positive 3 and negative 2, so I'm going to have x plus 3 and x minus 2. Now I'm ready to cross out my common factors, so I can cross out the x plus 3's. And now I can find the x coordinate of my whole. Remember, I take the crossed out factor in the denominator, which would be x plus 3, and I set it equal to 0, so that means x is equal to negative 3. So that's my x coordinate. Now I need to find my y coordinate of the whole. Now remember, I know I'm factoring this, but this is y equals. And now, in order to find my y coordinate, I first need to simplify this. So my numerator is 4, and my denominator is x minus 2. So in order to find my y coordinate, I need to plug in the negative 3 for this x right here, and that'll tell me what y is. So here we go. Y equals 4 divided by negative 3 minus 2. And that's going to be 4 over negative 5. So that's my y coordinate. So here's the ordered pair for my whole. Negative 3 and negative 4/5. Now let's find our vertical asymptote. Now if you remember, we take the part of the denominator that wasn't canceled out, and we set that equal to 0. So I will have x minus 2 equals 0, therefore x equals positive 2. So that's my vertical asymptote. Do you remember how to find the horizontal asymptote? Well, to do that, we need to look at the original equation. And so, first of all, I want you to look at the x term that has the largest exponent in the numerator. And in this case, it's 4x, and it's to the first power. Now, go ahead and look at the term that has the largest exponent in the denominator, and that would be x squared. Now, since the degree of the polynomial in the numerator is smaller than the degree of the polynomial in the denominator, that means your horizontal asymptote is y equals 0. Now, we actually have enough information so that we can graph this function. Let's start out by drawing our vertical asymptote. So I'm going to go over to where x equals 2, and I'm going to draw a vertical dashed line that goes through x equals 2. Next, I'm going to draw the horizontal asymptote, and that's y equals 0. So again, it's going to be a dashed line where y equals 0. Next, I'm going to draw a circle approximately where my hole is. So I'm going to go to the left 3, and then I'm going to go down 4/5. Now, that's really close to negative 1. Negative 4/5 is close to negative 1. So I'm going to put my hole right here. Now that I've drawn my hole, I can now draw my curve. And it's going to look something like that. And now we can draw the other curve that's part of this graph. And it's going to look something like that. Now let's go ahead and write our domain and range. Now I'm going to tell you that our domain is going to be tweaked just a little bit from our last video, and it's because of that hole. Now if you recall, if there was no hole, the domain would start over here at negative infinity, and it goes towards the right, but it cannot cross the vertical asymptote, so we have to stop at just before 2, where x equals 2, but then it picks up again just after where x equals 2 and continues to positive infinity. Now, because of this hole, that means the graph, remember this hole represents a point where there is no line. So our domain will start from negative infinity and it will go up to the hole. And then it will start on the other side of the hole and it will go up to the the vertical asymptote. And then it will start on the other side of the vertical asymptote and go to infinity. Now it will look like this. We start out at negative infinity and we go to the x-coordinate of the hole, which is negative 3. We're putting a parenthesis because it cannot equal negative 3. We use the union symbol, and now we pick up on the other side of negative 3. That's what the parentheses represents. And now we're going to go up to the hole. Up to the vertical asymptote, which is where x equals 2. We will use the union symbol again because we will pick up just after where x equals 2, and we will then continue towards positive infinity. Now we are going to do the same thing with the range. It's just that we are using the horizontal asymptote, which is y equals 0, and we're using the y-coordinate of the hole. So let's write that. Let's write the range. We start out with negative infinity, and we go up to the y-coordinate of the hole, which is negative 4/5. And then we're going to pick it up right after negative 4/5, and we're going to go to 0, the horizontal asymptote. We will pick it up just on the other side of 0 and continue upward to positive infinity. Now, this is going to take some practice, so let's try another one. In order to find our holes, or our hole, we first need to factor the numerator and the denominator. And when we factor the numerator, we get x minus 3 times x minus 4. And when we factor the denominator, we get x minus 4 times x minus 1. Now we are ready to cross out or cancel our common factors. In this case, that's x minus 4. So now let's rewrite what we have left. In our numerator, we have x minus 3. In our denominator, we have x minus 1. Now, in order to find the whole, we use the denominator that's been canceled out, which was x minus 4. So we're going to set that equal to 0, and that gives us x equals 4. Now 4 is going to be the x-coordinate of our whole. Now let's find the y-coordinate of the whole, and we will do that by substituting the 4 for the x, so that we have 4 minus 3 in the numerator, and in the denominator we have 4 minus 1. So 4 minus 3 in the numerator is 1, and 4 minus 1 in the denominator is 3. So our y value is 1/3. Now we can find our vertical asymptote. Now we look at the part of the denominator that was not canceled out. We're going to set that equal to 0. So x minus 1 equals 0. Therefore, x equals positive 1. And that's our vertical asymptote. Now for the horizontal asymptote, let's go back to the original equation, or the original function. And I need to look at the term that has the largest exponent in the numerator and the term that has the largest exponent in the denominator. Well, in this case, both of the exponents are 2. And when the degree in the top, or the degree in the numerator, equals the degree in the denominator, then the horizontal asymptote is going to be y equals, and it's this coefficient over this coefficient. And in this case, that's 1 over 1, which equals 1. So our horizontal asymptote is y equals 1. Now let's go ahead and write the domain, this time before we graph it. Now remember, we're going to start at negative infinity, and we need to look and see which comes first, x equals 1 or x equals 4. Well, x equals 1 would come first, so that means we're actually going to hit the vertical asymptote first. So I'm going to put negative infinity to 1, and then from 1 to the x-coordinate of the whole, which is 4, and then from 4 to positive infinity. And for the range, I will also start out at negative infinity, and this time I'm actually going to hit the y-coordinate of the whole before I hit the horizontal asymptote. So that means I'm going negative infinity to 1/3, and then from 1/3 to 1, and then from 1 to positive infinity. Now let's go ahead and graph it. First I'm going to graph the vertical asymptote, which is x equals 1. And then I'm going to graph the horizontal asymptote, which is y equals 1. And remember, it's y equals 1 because it's going through the y-axis where y equals 1. Next, I'm going to draw my hole as accurately as possible. I'm going to go to the right 4 and up 1/3. Well, that's not going to be very far at all. I know it looks like it's at 4, but we can imagine that it's at 4 and 1/3. Now, from there, I'm going to go ahead and finish my graph, or my curve. So there's one of them, which means my other one is going in this direction. Now, we really need to talk about the x-intercept and y-intercept. We need to talk about how to find them. But this has turned out to be a very long video, which all of this has been necessary, but I hate to add to this video. So I will make another one showing you how to find the x and y intercepts on rational functions. So I hope this video on horizontal asymptotes, vertical asymptotes, and holes, I hope this has been very helpful to you, and I look forward to working with you again. Bye-bye.